is Michael, and I'm going to be presenting my final report on the subject of fiber optical sensing. So, this is our table of contents. First, we are going to talk about the structural health monitoring using fiber sensor. Then, we have nuclear transistor integrity monitoring using quasi distributed fiber acoustic sensors. Then we will be talking about structural health monitoring based on long wave and distributed fiber optical sensor. Then we will be having the conclusion. And the first topic is structural health monitoring. These are the applications of fiber optical sensors in the structural monitoring that used to monitor landslides and earthfield dams and concrete dams and reinforced earth structures. Then we have pipelines that we can monitor using fiber optic sensor. Then in the particular study they have showed why they need to monitor the bridge. Many bridges have reached their end of design lifetime, so the goal is to ensure the safe operation, um, um, predictive and condition based maintenance. Then we have extension of lifetime, so this will increase the lifetime of the bridges. That way we can save our resources for better things. The fiber distributed optical sensing is basically divided into three. One is distributed strain sensing, which is the first one, and which is DSS. Then we have distributed temperature sensing, which is DTS. Then we have distributed acoustic sensing, which is DAS. The DFO's backscattering effect. So basically the fiber brag have three types of them. First we have a Raman, which is not sensitive to strain, static temperature sensing. Then we have Brilliant, which is temperature and strain dependent and static strain or temperature sensing. Then we have uh, Relay, which is temperature and strain in dependent and static and dynamic measurements. In the study they have the bridge model, which is a simulation one. The characteristics of the bridge model they've used in the lab environment is 2.5 meter length, then fiber glued on top and the bottom of the model. Then a possibility of different bearing. Then HDFO's measurement. This spatial resolution is 2.6 millimeter, and then the measurement rate is 50 gigahertz. This is the lab test that of the bridge model. Controlled execution of bridge beam. Single point vertical impacted followed by free oscillation. Then bearing. Left side is fixed bearing and the right is rotor bearing. Then we have the real time example of the bridge monitoring that is located in High Bridge in Austria. The bridges consist of steel and concrete composed bridge that have 7 spans and built in late 60s. Part of A13 barrier highway and part of European E45 route. That is the bridge have used by more than 2 million trucks per year. The load test on the highway bridge in the real time, the control load through two trucks, the temporary highway closure during night. The test load is two trucks weights 54 tons each. Truck stopped uh, uh, at a position in a bridge to monitor each span, like we have span 6 and span 7, the strain and distribution, upper beam with the lower beam, because they have two kind of beams. One is the upper side of the bridge and one is the lower side of the bridge. The inverse strain distribution, and the strain is 200 less strain on the upper fiber, and which means the lower beam have the more sensitivity than the upper beam. Then this is the dynamic strain measurement. Traffic flow measurement of the high frequency changes. Example, for according to the traffic flow, the measurement will change. Identification and classification of moving vehicles and velocity estimation. The conclusion of the first topic is FOS is beneficial for existing and new structures, localizing structural failures, and also FOS is a part of solution but not the only solution. Calibration of sensing cables is crucial in this environment. Then also, the path to moving forward is FOS has to become standard solution in tender standard, and guidelines are important for the FOS. Then prove advantage in successful case studies because of the real time studies. Then we have the second topic, which is nuclear transistor integrity monitoring using quasi distributed fiber acoustic sensors. This study is conducted by University of Pittsburgh. These are the studied they have done. They have electricity, grid transport and storage, and conventional and renewable generation. These are the distributed fiber sensing. For the infrastructure monitoring, we have multiple use cases for the distributed sensing. In this case, we have pipeline and slope, dam, tunnel, river, and ship, bridge. We can have all the things. Then we also have how the fiber colliding works. We have input light, and it forward the propagated light, and it back scatter the light, which have three types of reflection, as we seen in the first topic. We have Raman and Bilious, and then we have Rayleigh's scattering. This is a storage, nuclear storage, waste storage. The current status and importance of dry cask storage. Dry cask storage system for spent nuclear fuel are intended for temporary storage. In the US, many DCSS facilities are near the end of the initial licensed or certified terms. Licensed or certified terms may be renewed by the US Nuclear Regulation Commission for up to 40 years upon the submission and the approval of an application by the licenses. So the these are the current advancements in dry case storage. Consider inspections. First, we have the measured and corresponding FE simulated model shape. Then in the other picture, we have robotic inspection method using SS guidelines waves, axle wide. In the first wide, we have axle wide. Then we have circumfile wide. Then we have bottom wide, that used to inspect the storage container. This is the their proposed modeling scheme for physical modeling plus the fiber sensing plus the AI that they are proposing. First, we have active monitoring simulation. That then we have large number of numerical data set. Then we have multi-physical passive event simulations. And then they have experimental data, then they pre-process the data, then they have the controlled data set that used to train the convolutional neural network model, statistical feature extraction and feature mapping clustering, then data classification. Then they have active um, excitation of the data that can damage identification and classification that can be done by the CNN. And they have real time monitoring that for the passive events. Then also they can identify the event and the damage identification and quantification. This is the proposed monitoring scheme. Example, fiber optical sensor installation. We have sensor configuration that is rounded along with the pipe, and also that can be able to detect the gas leak and localization where it might have happened, and also generalized correction where it might happen. And also we have active integration uh, question. If for example, if it has some problem in the pipe, we can easily able to identify the problem through the proposed model. And we have passive integration, leak, environmental and security monitoring. For example, if the leak have found in the storage container, the model can able to tell the we can see the pressure impact loaded from the fluids to solid, the passive impact vibration waveform along the consistent surface. From here we can see that this is a improved structural coupling. This is for pressure field mapping. This mesh to interpret the where might be the fault happen. Then they have the data analysis approach, feature extraction and the AI based classification. They have time domain and frequency domain signal, and the feature extraction and mapping feature matrix. Then they have the CNN structure consist of feature map signal layer, then they have convolutional layer, then have the pooling layer, and again they have convolutional layer and pooling layer. Then it flatten to activation function. Then it can we can able to predict the um, fault detection. And then we can have data analysis approach, impact of noise of on classification accuracy. They proven that the model they have created worked better in all of the circumstances. And this is the experimental result to data selected acoustic sensing and platforms. They have included in the pipeline monitoring and also nuclear consistor monitoring. Then they have um, LCAT assist monitoring. And um, the third topic is structural health monitoring based on long gog and distributed fiber optic sensors. Strain sensor by gog length. We have discrete and distributed. In the discrete we have FBG, EFPI. Then long gag we have SOFO and FBG and microbent. In the distributed one we have Brilliant scattering and railing scattering. For the FBG sensor, this is how basically the FBG sensor will work. There will be a light input, and the FBG will brag a certain wavelength, and it will be reflect along with the path, and the rest of them will be transmitted. This is the typical application of how we can use. We have a structure, and then we have sensors. it can able to monitor the structures. Then we have central connection box, which channel switch, then the reading unit. uh, all of them will be inside the central measurement point. This is a global structural monitoring. uh, Structure is divided into parts called cells. For the bridge monitoring, each cell is equipped with a sensor combination called topology, which in the best manner corresponded to the expected strain field in the cell. And also this is the distributed sensing based on the scattering of a light into optical fiber. We have three kind of um, a scattering, as we saw first and second topic. We have Raman and Brilliant and ray light scattering. This is the distributed sensing. Distributed sensor can be repre- represented by a single cable which is sensitive at every point along its length. For example, we have the reading unit and we have the distributed sensor from 1 meter to 20 kilometer. So along with this line, it can be able to detect the temperature and also the strain. The distributed with discrete sensing. Distributed sensor is continuous and provides with a one-dimensional strain field monitoring. One distributed sensor replaces large number of discrete sensor with very simple connection. For example, first we have distributed sensor which have single connection cable simply connected to the reading unit. For the discrete sensor, we have sensor. For each sensor there will be multiple cables that helps to connect to the reading unit. So that's why we have large number of connecting cables that might be very not environmental friendly in some situations. Then we have integrity monitoring and for the distributed deformation sensor. For integrity monitoring, for the we can have the distributed sensor in the bridge and the tunnel, and for the dam monitoring. Then we have the examples of distributed sensor where we can be it can be used. First we have soil and a subjected to imposed ground displacement along with 50-degree fault line. So from the uh, monitoring table we can see how um, the can fault have happened here. For the example number 2, a bridge in Sweden, routine inspection in 1919. Large cracks and flags of steel uh, girders above the support columns cause fatigue over many years of service and the lower quality of steel. Then we have got bridges application. Single fiber optic single optical fiber per cable embedded in the uh, theoretical glass fiber reinforced composed tape that has that is installed in the bridge to monitor its strength, and also requires separate temperature compensation cable if temperature variants are expected, installed on the surface by glued and protected with aluminum tape to monitor the changes in the physical parameter of the bridge. Then last we have our conclusion. For the conclusion, FOS significantly enhanced structural health monitoring by enabling real-time accurate detection of structural failures in both existing and new infrastructures. Then combining optical fiber sensors multi multi-physical modeling, and AI improves structural health monitoring by simulating acoustic response and identifying defects through unique signals in both active and passive monitoring. Establishing FOS as a standard solution and ensuring proposed calib- calibration are essential for accurate and reliable structural health monitoring data. And then the initial experimental with FOS such as mock Cassia facility and multimode interferometers show practical application for monitoring acoustic and vibrational signals. Future efforts will optimize hardware and conduct field testing to enhance real-time structural health monitoring, aiming for improved protection and guidance on the sensing networks. That's it for my final presentation. Thank you for the opportunity to present my final presentation here, and thank you.